Is it live? So, is my voice audible, Nika? And live stream, everything is perfect, like? Great. Okay. Good afternoon, everyone. Welcome to another lecture of digital design and computer architecture. I'm Mohammad, one of the instructors of this course. Finally, I got the chance to teach some lectures, and I hope you guys enjoy this lecture. So today we're gonna learn about one of the advanced topics in computer architecture that almost all modern architectures, processors, they are using out-of-order execution. And this is quite important in order to provide good parallelism for execution. So we're gonna see a lot about it, hopefully today. And next week, also, we're gonna continue our lectures on advanced computer architecture topics. We're gonna learn about GPUs, for example, next week on Thursday. Okay, so basically, prior to last week, we discussed microarchitectural fundamentals. We learned about single cycle architectures. And last week, I think you guys had learned about pipelining, like how we design pipeline processor. And also you learn about control and data dependence or data hazard and how we can handle them. Today, I'm gonna continue a little bit about pipelining related to precise exceptions, because this is quite important to understand this lecture very well. And then we will jump to out-of-order execution, how we basically do out-of-order, and basically how we can make sure that things can execute out of order, but still correct. So, which is quite important. So for the readings, these are the reading that you had for past weeks and also today. For this week also, we're gonna use these readings. So if you are interested to learn more, you can check these readings. Okay, so basically what you have learned from microarchitecture is first was single cycle, that we run each instruction for the whole cycle. And then we try to do better and we make a pipeline processor. And basically, so we chunk execution of instruction into several stages in order to reduce the clock cycle time. And basically we design pipeline processor. But in reality, in most of today's architectures, actually we have multi-cycle execution. So that the amount of cycles that take to execute each instruction or each arithmetic instruction is different. So for example, for simple arithmetic operation like addition, it may take like only, let's say, 1 cycle or 2 cycles. But for more sophisticated arithmetic instructions like multiplication or division, or maybe floating point instructions, they may take several cycles. So we don't really design ALU in this today's architecture, like an ALU that takes only 1 cycle. And if you need to actually make that cycle long enough, such that, for example, you can do division. But this long clock cycle time is actually too long for simple arithmetic operation like addition. So because of that, we have kind of multi-cycle execution. And as I said, not all instructions take the same amount of time in the execute stage. And we're gonna have multiple different functional units that take different number of cycles. So so we haven't covered actually multi-cycle execution in this course this semester, but that's the only thing you need to know, that basically the execution part can actually take several cycles. It doesn't need to be only 1 cycle. So this is an example that, for example, after fetching an instruction and decode, depending on the type of instruction, we can actually dispatch to different execution line. For integer addition, we may have only 1 cycle for execution. For integer multiplication, we have 4 cycles. For floating point multiplication, we have 8 cycles, and so on and so forth. And so this is the architecture that we want to achieve in multi-cycle. So it can be pipeline or non-pipeline. So today we're gonna only focus on the pipeline design of such a multi-cycle processor. Okay, so yeah, let's see with this example. So here we have several instructions that you can see in the left side of this slide, like division, then addition, division, and addition, and some also instructions in between. And we have, basically, we make a simple pipeline using this concept of multi-cycle. So for example, the division is gonna take like 8 cycles for execution. So we basically fetch, decode, and then we move to the execution for 8 cycles, and then we write back. For addition, it only takes 1 cycle, so we do fetch, decode, 1 cycle execution, and then write back, and so on and so forth. So this is the pipeline processor that we design, kind of. Can you guys tell me if this works correctly or not? Is there anything wrong with this kind of design? Yes?
So how can there be multiple instructions in the same stage?
So these stage, you mean execution stage, right? But these are relatively different. So we have different functional units. So we have, for example, we have a functional unit for doing division. And when we call it, basically when we are in division, we are using only that functional unit. So it's not actually the same stage. So there is nothing wrong in that sense. But actually there is something wrong with this kind of design. But I still, I like to wait a bit more. Last chance. Think about von Neumann model and sequential ordering of executing instructions. Are we executing instructions sequentially here or not? From the programmer perspective. Yes?
No, because there are no dependencies. They don't depend on each other.
Yes, kind of. And also, yeah, you can see that, for example, the instruction, so basically after write back stage, our instruction is done. That, or we call it, the instruction is retired or committed. So basically the addition instruction is committed before division instruction. So that's wrong. From the programmer perspective, everything should actually be committed in order of the basically the sequential of order of instructions in the program. So basically the division instruction, since it takes longer here, so it's committed very long, very after other instructions, which is wrong. So this actually, yeah, basically it is wrong based on the von Neumann model. As you can see that these are instructions that they are committing earlier than the division. So now this is the sequential semantics of the ISA not preserved. And the problem is that it complicates, first of all, it's wrong based on the von Neumann model. And why is wrong? Because it actually complicates the debugging step. And also it complicates how we can recover if something went wrong in your execution. For example, in division, imagine that so here you want to basically divide R1 by 2. So imagine that R2 is 0. So you have division by 0, right? So this should not be done. This kind of considered as exception that we're going to see soon. This is division by 0, which should not happen, right? So it's an exception. So normally your code should not actually continue normally after this division, because division was not correct, because it was division by 0. But if we don't, preserve the ISA, and so we don't know the order of execution, what are the instructions that have committed or not, basically we don't know how to recover from the state. So basically this is wrong, and we want to make sure that things are gonna kept, the things, instructions should be committed in order, and we're gonna see how. Okay, but before that, let's quickly talk about exceptions and interrupts. So basically, exception and interrupts are unplanned changes or interruptions in program execution. It can be due to internal problems in execution of the program that we call them exceptions, and can be also due to external events that need to be handled by the processor that we call them interrupts. So both exceptions and interrupts require basically, so let me give you some examples. So for exceptions, we're gonna see more examples in the next slide. But for exception, for example, division by 0 is one exception. For interrupt, whenever you get an input from I/O device, for example, you enter a key on your keyboard, and this key should be processed, for the processor. So that's considered as an interrupt. That basically whatever processor is doing should be interrupted in order to service that request from you. We're gonna see more example of them also later. These exceptions and interrupts, they are both require a stopping of the current program. So whatever is running, so we need to stop it. And then we need to save the architectural state. So basically the status of the registers, program counter, whatever you have in your processor, like that they are important to resume your execution. So all of them needs to be stored back. And then you need to somehow handle the exception or interrupt. So you need to switch to the handler, let's say. And then if possible, you can basically, and make sense, we need to return back to the program execution. Sometimes exceptions are kind of, happens that stop the execution of your program completely. So your program needs to be terminated. But sometimes you can actually trap exceptions and somehow solve it. For interrupts, mostly we get back to the normal execution after servicing the interrupts. So now let's see some examples. For exception example, like, as I said, like divide by 0, overflow in your arrays, for example, undefined opcode, general protection or access protection. For example, you access a part of memory which is not under your privilege. So that's kind of exception. Page fault, which you will see actually in the last lecture about virtual memory when you see, but this is related to DRAM access. And for interrupt example, as I said, like I/O device needing service, like keyboard input, video input, periodic system timer expiration, power failure, machine check, and so on and so forth. So for example, when you have a kind of a power failure, sometimes sometimes we still have some power, to make sure that we don't lose everything. So it's kind of considered as an interrupt, that all states of the registers and the architectural states needs to be saved before turning off your system, basically. So it's the kind of prediction of the power failure. But sometimes we are unlucky and the power failure is sudden and you cannot really handle it well. Any questions, by the way? I mean, feel free to interrupt and ask questions. I will make sure to take interrupts. Okay. So exceptions and interrupts are very much the same. I mean, in many cases, but they are also a bit different from the philosophy concept. So the cause of exceptions is usually internal to the running thread. So one thread is running and some exceptions happen for that. But interrupts are usually external to the running thread. The difference actually causes this event to handle. So for exceptions, usually whenever it happened and we detected an exception, we need to basically handle exceptions. But for interrupts, when convenient, most of the time, you can actually delay taking interrupts. For example, you ask a question, and I'm in the middle of the important topic, so I can delay a little bit until I take your question. But sometimes something is so urgent, we cannot really take that time. So most of the time is when convenient, but except for very high priority ones like power failure, machine check error, or something like that. So if you want to think about priority, is always processor exceptions. And for interrupt, basically, it depends, as I said. So for handling context, so for exception, usually the process needs to handle it. So I think, have you ever write a code like trap handler? I remember in Java, we were writing some code like trap to handle exceptions. Anyone? Okay. Yeah. So yes, for exceptions, actually, you have this possibility to, you know, to implement it in the process, to have some code, you know, to handle it the exception nicely. For example, if you know, if you are programming a calculator, and a person basically try to do you know, divide by 0, your software should not basically get crashed, basically, right? The software should provide a meaningful message that, yeah, basically the divide by 0 is not defined, so please use something else. So that's the job for the programmer, to handle exceptions nicely. But for interrupt, usually is handled from the system, from the operating system. We are not going into detail of them for sure today, but just to give you some, you know, overview of them. So yeah, so basically the architectural state should be consistent. When we move to precise exceptions and interrupts, this is the rule, that architectural state should be consistent or precise when the exception interrupt is ready to be handled. Which means all previous instructions should be completely retired. So before taking basically exceptions, we need to make sure that all previous instructions should be completely retired or committed, and no later instructions should be retired. So there might be some instructions in the pipeline, because you have a pipeline processor. You need to make sure that none of them are going to retire, such that you know that from which point you can continue your execution when you resume from exception handler. When I say retire, it means commit, which also means finish execution and update architectural state. Basically, when we talk about committing instructions, we really mean that, okay, to inform the programmer about the finishing of this instruction. So this is important to take into account. So yeah, so for example, after this division, we have this precise state that we need to have this clean separation of sequential instructions. So in single cycle processor or pipeline, this is really easy to implement, because you have this instruction-based scheduling, like single cycle scheduling. So you always know that per cycle, what the instructions that they are in the pipeline. But when you have multi-cycle execution, you need to be more careful to how to handle it. Okay, so basically, to checking for and handling exception in pipeline, we need to, when the oldest instructions ready to be retired is detected, that they have to have cause and exceptions, the control logic. So we need to ensure that architectural state is precise. So register file, PC, and memory. We need to flush all younger instructions in the pipeline. So whatever we have in the pipeline and they are not close to retire, we just flush them. And we need to save a program counter and registers as specified by the ISA. And then we redirect the fetch engine to the appropriate exception handling routine, or let's say interrupt handler. So this is actually, for example, from the ISA x86. I think this semester you learned about MIPS ISA. x86 is also well-known Intel ISA. So in this paragraph, for example, they talk about precise exception, that I'm not going to read it for you, but just very similar to what I said. So before taking an interrupt or exception, you need to make sure that you have a precise state for your PC and basic architectural state. And younger instructions that they are in the pipeline, they need to be flushed, and such that you know where to resume. Okay. So basically, it's important to have precise exception, because it's actually the semantics of the von Neumann model. And so it's important when we get back to from the exception, when we get back to the normal execution of the application, we need to know that from which point we need to continue. And that's That's very important from the mindset of a von Neumann model. And von Neumann model is different from data flow machine. I think we haven't talked about data flow machine in this semester at all. I will briefly describe data flow later in this lecture, but not now. So it's also, it's good for software debugging and enable easy recovery from exceptions, enable restartable processes, and enables traps into software. As I said, like the software implemented opcodes, that whenever exception happens, you can write some codes like traps that take those exceptions and do meaningful stuff for your program. Okay, so let's get back to this example. We have this execution and we designed this pipeline, and we saw that basically since we are committing instructions out of order, when exception handle for that division, basically our status is not precise. And now we want to know how we can fix it. So one simple idea is actually, take as enough number of cycles for all instructions. Like for example, for division, the number of cycles for execution is like 8 cycles. I'm gonna consider again 8 cycles for addition as well. So yeah, this can solve the problem, but for sure this is not an efficient solution, right? So because the main idea of going through the multi-cycle execution is that for those instructions that I don't need to spend like 8 cycles, so I'm gonna spend only 1 cycle or 2 cycles. So this way I'm gonna spend all the cycles for all the instructions, and definitely it's not really good. And the worst case instruction latency determines all instructions latency, basically. And here, in our example, we have only division, kind of. The latency of division is longer compared to in addition, for example. But we have also memory operations. That memory operation might be so long, like tens of cycles. And so for them, the issue might be actually even worse. Okay, so the solution to this is providing reorder buffer, which we're gonna see today. There are also some other solutions to this problem, like history buffer, future register file, and checkpointing, that we are not gonna cover, but you can actually watch them from the past lectures if you're interested, and also from the reading that we have in this slide. So, what is reorder buffer? The idea is that we complete instructions out of order, meaning that we execute instructions out of order, but we reorder them before making results visible to architectural state. Meaning that before committing the instructions, things should be reordered, and things should be committed in the order of the program semantic, the program sequential order of the program. So that's the job for reorder buffer. So yeah, basically when instruction is decoded, it reserves the next sequential entry in a special buffer called the reorder buffer. And when instruction completes, it writes the result into reorder buffer entry. And when instruction oldest in the reorder buffer, and it has completed without exceptions, its results move to register file or memory. So which means that we do the write back basically step. So it's quite simple. After we know it, it's quite simple. So so when we decode instruction, we reserve an entry in reorder buffer for every instruction. And when an instruction finishes the execution, it writes the output in the reorder buffer. But just in the reorder buffer, it's not transferred to the main memory or to the register file. When that instruction is the oldest one in the reorder buffer, and it's completed without any exception, then we can actually write back to the register file and basically remove that entry from reorder buffer. Any question? Okay. Is it that clear? Yes? So That's a very good question. First of all, I mean, weaker memory, you mean weaker memory model? That's not really related to this topic. And that's actually related to consistency model. If you're, I don't know if you're, I think, okay. But anyway, it's always things that, you know, as a, so we have always this architecture, hardware and software, you know. We can always try to, you know, make less conditions for the processor to make the processor easier and probably faster. But, and put the whole effort on the programmer to make sure that, you know, programmer, I mean, they should handle it. Good luck. But this is not, this is, can be one of them. The other way around is that, you know, put everything on the hardware and make the life for the programmer so easy. So most of the successful architectures that we have today, they are kind of in the middle. So some processor, they try to, you know, make some changes, some benefits, as well as some constraints that programmer needs to basically obey those constraints. Or when I'm saying programmer, it can be also compiler. Doesn't need to be programming, but they need to obey those. But if we put too many conditions, then it's also not that good. So it's just about, you know, a trade-off, design points that we want to make things good for both hardware and software. Yeah.
What is if we have an instruction that takes quite long and is therefore not in the reader buffer, but we are already starting new instructions which are dependent of this result?
Okay, so that's exactly out of order execution, but we haven't visited yet. So here we still is in order dispatch. So you cannot really put the instruction that's coming after your long instruction to the pipeline, because dispatch is always happening in order.
Yeah, but if it takes, I mean, we have multiple functional units. If I have first to like an add or like a multiplication,
yeah,
then I want to use that result in the next instruction, which is a simple addition.
Okay.
Then I have a problem, right? Because the multiplication hasn't finished yet, so I can't start the addition.
Yes, and that's a problem of this pipeline. I mean, this is in order pipeline, right? So in order pipeline is in order. Yeah. So we'll see about how we can handle it soon in later slides. Okay. So this reorder buffer is a hardware structure that keeps information about all instructions that are decoded but not yet retired or committed. What we have in reorder buffer is, I mean, some entry can be like the valid entry, that this entry is valid or not. We can also have like destination register value, destination basically memory, about the value that you want to write to the memory. The top of reorder buffer considers the oldest instruction that the pointer to the, so the pointer to ROB entry contains information about the oldest instruction in the machine. And also we have this youngest instruction. So, and ROB is implemented as a circular queue in hardware usually. So it's like a queue that's kind of circular that you push NQ and DQ instructions or entry to that. So we have lots of information in ROB entry, as I said, like valid register ID, destination, store address, store data, PC, and so on and so forth. So all these information are required to correctly reorder instructions back into the program order. And we update the architectural state with the instructions results if instruction can retire without any issues. And it's important to handle an exception and interrupt precisely. If an exception interrupt needs to be handled before retiring the instruction. So we need valid bits to keep track of readiness of the results and find out if the instruction has completed execution. So yeah, so basically we need to, you know, keep a lot of information in each ROB entry just to track the completeness of instructions and realize that if it completes without any exception happens. So with this reorder buffer, what we can do is actually, we can add a step like R, which call it like reorder. So each instruction, after finishing the execution, it actually writes to the reorder buffer. And then we delay the write back step until basically the oldest instruction in the reorder buffer write back. So the division instruction was the oldest one. So we need to wait until this one writes back. And after that, we can write back the other instructions. So now we actually obey the, we obey the von Neumann model, as well as, I mean, not only von Neumann model, this sequential order of the instructions in the program. And yeah, and we have precise exception handle. So here we actually, as you know, we need to stall the pipeline because, so when a later instruction needs a value in the reorder buffer, which is not prepared yet, we need to basically stall the execution. It's very similar to the data hazard of read after write. So you need to read the data, which another instruction is going to produce that. So we need to stall the pipeline until that value basically gets ready. Okay. Yeah, so reorder buffer also, we can try to forward things from reorder buffer. So I think you learn about forwarding passes, right, in the pipeline. That we can forward the data from execution step to the, for example, decode step. This is also possible that you can actually mix, have register file and reorder buffer, as well as bypass passes that basically the operands to the functional unit can come from the register file or from the reorder buffer or from the bypass passes. So that complicates the hardware, but at the same time makes possible that you stall your processor less frequently. Okay. So we have an example here that we are not going to run it here. I mean, you can actually fill this register file and reorder buffer at home if you're interested. This is the code that we want to run. Multiply. We have 2 multiplication and then 2 addition. And this is our reorder buffer and register file. You can consider that all registers are valid in the initial step, and reorder buffer is completely empty. So you can actually try to, based on the assumptions that we had, like multiplication takes 4 cycles, for example, addition takes 1 cycle. You can actually try to, make a pipeline and fill up this register file and reorder buffer for this simple application. But yeah, as a optional homework if you're interested. Okay, so in reorder buffer, when we want to access it, which I forgot to mention, in reorder buffer, it's actually content addressable memory. So we need to search with register ID, but register ID is actually part of the event. I mean, the part of that entry in the reorder buffer. In register file, you have the register ID that you can use that ID to, to indirect access. So when you want to access register file, it's like indirect accessing. It's very similar to how you access your DRAM or SRAM. So you provide address and get your value. But for reorder buffer, in this example, it's content addressable memory. So you really need to search all the basically entries and check your and compare the register ID that you are looking for with the register ID which is stored in that reorder buffer, which makes it so slow, right? So if you have like 64 rows in reorder buffer, which we have actually much more than that, you need to search it like in parallel or serially. In parallel, it causes a lot of hardware cost, and serially, it causes a lot of latency. So in order to fix that problem, we use indirection as well for reorder buffer access. So when we access register file first, we check if the register is valid. And so if register is not valid, register file stores the ID of the reorder buffer entry that contains or will contain the value of the register. So we give some ID to reorder buffer entries, and register file actually stored that ID for that register. Do you have a question? Yes.
Sorry, when is the register not valid?
For example, we have dependency, you know. Okay. Yeah, exactly. Yeah, so the register file stores the ID of the reorder buffer entry, and then we can then use the mapping of the register to the ROB entry. So now that you have the basic kind of the address of the entry that you need to read from reorder buffer or you need to access, then you can easily access it. So you don't really need to go through all the entries of the reorder buffer one by one. So you have an address and you just select it. Similar to how you access your main memory, your register file, and so on and so forth. So yeah, so we access reorder buffer next, and now reorder buffer does not need to be content addressable, as I said. Okay, so register file now needs to actually have store a tag, which is a pointer to the ROB entry. So in this architecture that we have reorder buffer, we also need to add this tag entry to the register file, which is the pointer to the ROB entry that has or will have the result of that instruction. Okay. Any question? Good. So I'm going to start with, okay, I think, yeah, I will take this and then we can take some break. So now that we want to see how we can basically add this reorder buffer to our pipeline. So this is a data dependence type that you know from the past lecture. Yes.
For a register file, does this mean that now a register is more than 32 bits?
Yes, exactly. Yeah. I mean, your data register can still be 32 bits or 64 or whatever, depending on the ISA. But you need to add some other kind of, let's say, registers or something to that level. Or you can consider a register which is bigger. But yeah, I mean, what I'm trying to say is that they can be separate registers or they can be connected to each other. In the end, it doesn't really matter. No, did you get what I'm trying to say?
So they can be multiple registers? Or?
Yeah. So, I mean, in the design, you can consider that you have a bigger register, like, let's say, 128 bits wide register, and then use it for tag and data and so on and so forth. Or you can have multiple registers. But all these multiple registers can access with the same, basically, address. Okay, so this is the flow dependence that I think you have seen in last lecture about read after write. So here we have two instructions. That the second instruction is actually dependent to the first one because we are reading from register 3 that this register is going to be updated by the first instruction. So we have this read after write. But we actually have two more other data dependencies that I think you haven't seen last week. So they are important actually for such architecture that we have multi-cycle execution. These are actually anti-dependence because they are not really, they are not real dependency. We'll see why. So this one is write after read dependence. So the first instruction is reading from R1, and the second instruction is actually updating R1. So if you have, if you execute things in order, I mean, without, committing things basically out of order, things should not be a problem, right? So basically, this one is you will first finish this instruction. So when you want to start decode this instruction, you will read the R1 value, and this instruction, the value of R1 is going to be updated after R3. So it's not going to be a problem. But in but when you have out of order execution, this might be a problem that we have right after read dependency. And another dependency, which we call it output dependence, is right after write. So you have these two writes to R3. So again, the problem is that after all, basically R3 should have the value of the last instruction. But if you don't handle things right, R3 might be, might have the value of the first instruction because you are trying to execute things out of order. So we call them, actually, these are anti-dependence because they are not really real. And the reason is that the reason that we are using the same register here, R1 and R1 for the anti-dependence, and also, again, we use R3 for this output dependence, is that we have limited number of registers, right? So imagine that we don't have that limitation and we had whatever we need, infinite number of registers. Then we wouldn't have this problem, right? The third instruction can easily write the result to, I don't know, R1000, right? It doesn't need to be R3. So the reason that we have dependency here is that we are writing both instructions to R3. But for the flow dependence, it's actually a true dependency. It doesn't really matter how many registers you have. Whatever you have, that dependency is there. Because the second instruction, you need the value which gonna produce by the previous instruction. So it's like a producer-consumer model, which you have basically dependency. So we can actually use this reorder buffer with register renaming. That's in order to resolve this kind of dependencies. Yes.
What makes the write after write instruction different to the write after read and read after write? Because there is like this gray line in between, and isn't it just a problem that we have like a write after read there?
So write after write is writing to the, you have two writes that you're writing to the same register. And write after read is, so you're writing to the register that you will read, that you read from that register in the past, or you should have read.
Isn't write only a problem if we read it like in between?
I'm not sure, not necessarily, I guess. It really depends, yeah. Yeah, I'm not sure. I don't think actually it's really important to have that gray instruction in between. Yeah.
Yeah, okay, that makes difference what is at the end.
Yeah.
Which is actually good.
Exactly. Yeah. So, yeah, as I said, output and anti-dependencies are not true dependency because the same register refers to the value that have nothing to do with each other. And they exist due to lack of register IDs or names, let's say, in the ISA. So what we do is just, the register ID is renamed to the reorder buffer in tree that we will hold the register's value. So register ID get the ROB entry ID, and architectural register ID, we get to the physical register ID. And after renaming, ROB entry ID used to refer to the registers. So yeah, let's, I think I will have an example later about it to clarify more. But for example, what I can say here that when we reserve, for example, for this output dependence, when we want to decode this first instruction, R1 to operand R2, so we reserve an basically reorder buffer. And so there is an entry name for that reorder buffer, right? And then we can use that entry name, like the value or the address or the ID, to rename this R3 register. So we don't really, so when we want to talk about R3, in between, we don't really talk about R3, like the exact name. We talk about the renamed registers. We will see with the detailed example, like the walkthrough example later, that you can fully understand what I mean. But just the concept is very simple, that we rename things to make sure that we don't update the same thing twice. Okay, so this actually elements anti and output dependencies and give the illusion that there are large number of registers. As I said, if we have large number of registers, we don't really have write after write and write after read dependencies. Okay, so here was also another example that is for your homework, if you are interested, as an example that you can do at home. Okay, so now in our pipeline, in order pipeline with reorder buffer, we have decode step that we need to, so basically we access register file and reorder buffer, and we allocate entry in the reorder buffer and check if instruction can execute, or if so, dispatch instructions. We have execute a step, which is instructions can complete out of order. And then we have this completion or reorder buffer, we call it R, that we write result to the reorder buffer. And then we have a step of retirement or commit, which we call it write back. So we check all this instruction for executions, and we write results to the architecture register file or memory. And then we can flush pipeline and start from exception. And if we have exception, we can flush pipeline and start from the exception handler. So in order dispatch execution and out of order completion and in order retirement. So this is the pipeline that we designed until now. So reorder buffer is conceptually simple for supporting precise exceptions and can eliminate false dependencies, but it also has disadvantages. So reorder buffer needs to be accessed to get the result that are yet to be written to the register file. So we have this CAM or indirection, which in the end increase the latency and complexity. You need to access a lot of memory structures during the execution of your instructions, which is costly. So there are also other solutions like history buffer, future file, and checkpointing that, as I said, will not cover. These are some lectures from Professor Mutlu in the past that you can actually check to learn more about this concept. Yeah. I hope you can understand it. Anyway, so these are also some lectures from 2015 that you can watch if you're interested. And also we have some backup slides at the end of this lecture about precise exception that we can see. Okay, so before going to out of order execution, let's have, if you let me only 8 minutes break, I'm sorry, we are a bit late, I'm running out of time. So let's get back at 3:10 and we will continue with out of order execution. Okay, so there was one question in the YouTube chat that was actually the question for one of your colleagues as well. So I'm gonna explain it a little bit more. So basically, in our example that we mentioned, like we have some instructions. The first instruction was division. And we say that basically if we have divide by 0 and we have exception, so basically how we make sure that things are precise. So the trick here is that when you decode instruction, you basically allocate entry in the reorder buffer. And other instructions, when they finish the execution, they write to the reorder buffer. And they don't write to the register file until the oldest instructions get retired. So the oldest instruction in the reorder buffer is this division. When it's basically finish the execution step, it can naturally, I mean, it can theoretically, let's say, get retired. But the problem is that it might happen that we have divide by 0. So here, if exception doesn't happen, we basically write to the reorder buffer. And since this instruction is basically the oldest one, we just write back. And then we can keep going to the reorder buffer. But if the exception happens, so we don't really write back. So these instructions, we basically go to the exception handler. To the exception handler because of that divide by 0. And we don't basically retire entry from reorder buffer. And younger instructions that we have in the pipeline or in the reorder buffer, they all needs to be flushed, because I mean, in the end, we are not going to write back them, right? We need to repeat things if needed, if it really makes sense. Okay. No, not this one. Okay, so this is our in-order pipeline that we built together. That basically we dispatch like act of sending an instruction to the functional units, and we rename using reorder buffer element, and that element stalls due to false dependencies. But we have a problem that a non-ready instruction can stall dispatch of younger instructions into functional, like execution units. Basically, for whatever reason, there are some instructions that they are not ready to be executed. So they can basically stall the dispatch of younger instructions. So here is an analogy that is actually coming from Professor Mutlu. So you can see that this tram, for some reason, is a long latency instruction that stalls the pipeline. This tram is broken that time, 12:55. And you can see that there are some other trams, cars, like instructions that they are independent. Actually, this one is tram 11, and that one is tram 5, and they are already independent on the line. But from this line, they are dependent, and they can basically tram 5 needs to wait for tram 11, and this car also. And this is also another view that this tram stalls the pipeline. It's another view. Another view that still we have that stall. And yeah, finally, basically stalling done, and independent instruction gets time to execute. But you can see that, yeah, tram 5 is moving. So that's the way that we want to get rid of these instructions. So whenever we want to have a kind of capability that whenever an instruction is long latency, and for some reason it stalls the pipeline, we just want to put this instruction aside and ask them to wait. And then we should be able to continue with other instructions that they are independent. Of course, with tram, it's not really easy to put it aside. But for instructions, hopefully, it's much easier. So yeah, basically, this is the way that we want to do in this lecture. So we have these two pieces of code. They are almost the same. The only difference, I guess, is only the first instructions. The first one is multiplication, and the other one is load. So the first addition, you can see that this one we have true dependency, right, to the first instruction. So the first instructions produce result to the R3, and then addition instruction is going to use that R3. So we have this true dependency. Since for the addition, the first instruction, the first add, it needs to be wait and it stalls the whole pipeline because we have in-order pipeline. So basically, addition cannot dispatch because of its source register, and later independent instruction cannot get dispatched. So you can see other instructions like addition, these are all independent, but they cannot get dispatched. So the thing is that things can get worse when we have load instructions because the latency for them is quite variable. We're going to see a lot why in next lectures. I think on Friday, maybe somehow, and some other lectures. Next Friday. But yeah, so basically the latency for load instruction is quite variable, and then it can complicate things even more. So, and this is important, you know, when you have fixed kind of latency for some stalls, you can actually think of supporting at the compile time. So when you are compiling and you see some independent instructions, you can try to actually reorder them. If the semantic of the program cannot be, I mean, is still kept correct. So the compiler can actually do some reorder. And actually modern compilers are trying to do that. There are also some compilers that they try to sever, I mean, aggressively do that in VLIW processors that I don't think we have time to cover them. But yeah, basically, but for those instructions that the latency is variable, like the load latency, things are really hard to handle at the compile time because you really need to verify it at the runtime, the microarchitecture. Okay, so yeah, so we want to get rid of this problem in order dispatch and scheduling or execution, and the solution is out of order dispatch. So the basic idea is very similar to data flow machine. So in data flow is actually another, let's say, paradigm of execution that basically you don't really care about the order of instructions. The only thing that important is for you is that if the operands are ready for that instruction or not. So in data flow, the terminology is fire. So we fire an instruction only when its inputs are ready. That's the only criteria you have. You don't really care about the order of instructions that program defines. You have a data flow graph. And for every instruction, the only thing matters you is that are the operands ready or not? If they are ready, you just execute. Which is beautiful, right? You can provide huge parallelism, but it's also very hard to program and compile and debug. So in this out of order execution, we will get to something like data flow machine. I mean, to some certain, but we'll see. There are also some other ways to prevent dispatch stalls. One way is actually compile time instruction scheduling and reordering. So here we are trying to do out of order execution, which is dynamic scheduling of instructions. But it can be also at the compile time that you schedule instructions and reorder them at the compile time. But I already mentioned the difficulties of that, right? For some instructions, the latency are variable, and it's very hard to assess how to schedule them nicely. I mean, there are some architectures that they actually try to do it aggressively, as I said. Another way is that you do value prediction. Whenever you have some dependency, like read after write, you predict the value, let's say 0, and then you continue. And if your prediction was correct, then okay, you managed to fix a lot of, to get a lot of performance. But if your prediction is wrong, you need to basically redo things. So it's really important to, how to predict values is actually a very tough problem. And many prior works have been looked into this problem. We also have a recent work that's going to appear in this year ISCA in early June, that we look into this problem, actually, value prediction. And another option is to use fine-grained multithreading. When you have many threads in your pipeline, like from different process, or simple process, but they are similar process, but they are different. And you can just quickly switch among these threads. We're gonna see about fine-grained multithreading briefly, actually, next week on Thursday, when I want to talk about GPUs, hopefully. Okay, so, but in this lecture, we only care about out-of-order execution, which is dynamic scheduling. So the idea is that move the non-ready instruction out of the way of independent ones, such that the independent ones can dispatch. So we monitor the source values of each instruction in the resting or waiting area. And when all source values of an instruction are available, we fire or dispatch the instruction. As you can see, it's very similar to out-of-order machine. So, yeah, so they are these instructions dispatched in data flow order, not in control flow order. And the benefit is that it provides a lot of latency tolerance. I mean, it provides a lot of parallelism, right? So you don't really, so whenever there is an instruction which can be executed and is independent, you just pick it up and execute. And it can actually provide, for sure, latency tolerance. So you can actually hide the latency of your stalls by executing useful things. Question? Okay. So yeah, this is in-order versus out-of-order dispatch. Basically, in our in-order dispatch plus precise exceptions, we have this kind of pipeline that we fetch, decode, and then we execute. The other one, fetch, decode, and then we need to stall because we have this in-order dispatch. And also the second instruction also needs to stall because the first one is basically, again, we have this in-order dispatch. And this is the whole latency of the pipeline. But in out-of-order dispatch plus precise exceptions, we can actually keep running. So this instruction, for example, the third one, which was independent, we could so execute it and actually so write the results in the reorder buffer and then write back in the end. So with that, we can actually reduce the latency from 16 cycles to 12 cycles. So the benefit of out-of-order execution, it really depends on your program, and people report different, basically, performance improvements among something around like 50% can be, or even higher in using some other, basically, improvements. Okay, so how to enable out-of-order execution? We need to link the consumer of a value to the producer. That's the key, because we really want to know which instruction is producing the value that we are waiting for that. And we need to buffer instructions until they are ready to execute. And instructions need to keep track of readiness of source values, which is, again, the key part of the data flow machine. And when all source values of an instructions are ready, we need to dispatch the instruction to its functional unit. Okay. So in order to link the consumer of a value to the producer, we use register renaming. So we associate a tag with each data value. We're going to see in a picture soon. To buffer instruction, we define a topic named reservation station that basically we insert instructions into reservation stations after renaming. So when an instruction is done, we broadcast the tag when the value is produced. So when an instruction is finished the execution and produce the value, we need to broadcast the tag to the whole basically memory structure that we have inside the processor. And then instructions need to compare their source tags to the broadcast tag. And if there is a match, then basically that source value becomes ready. And when all source values are ready, basically we need to wake up instruction and basically send it to the execution. So this idea actually has been invented by Robert Tomasolo, out of order execution with register renaming. It has been used actually in IBM 360 only in floating point units. If you want to read about the paper that Tomasolo wrote, you can actually check this IBM journal. But basically, what Tomasolo hasn't basically, I mean, people in those days in IBM, they haven't prepared is that they try to get rid of precise exception. So they don't have this reorder buffer, and as a result of that, they don't have precise exception handler. And later on, people basically added precise exceptions in later works, and they basically make it more useful. So IBM 360 was actually quite, I mean, very good for research because they make a lot of developments in research, but sadly from IBM was not really useful in terms of financial things because they couldn't really earn a lot of money from that, as I said, because people couldn't really program and write for that machine since they haven't provided this precise exception. Precise exception is really important for, as I said also in the past, for debugging. So if you don't have precise exception, writing a code for that machine is just a headache. Okay. So yeah, so we have two humps in a modern pipeline. So we have fetch and decode. And then we have the first hop, which is reservation station or scheduling window. And the second hop, which is reordering, that reorder buffer, also known as instruction window or active window, that after execution, you need to use it. And after that, you have this write back. So fetch and decode are in order. And then execution is out of order. And then we have this write back, which is in order. It's also another analogy when you want to think about two humps in a modern pipeline. So we have this scheduling and reorder. Okay, so this is a general organization of an out-of-order processor. So there are many blocks here, but what I'm trying to emphasize here is that this block, which does decoding and renaming and for dispatch, and you have reservation station, basically, and you have functional units for basically different types of instructions. And here you have reorder buffer to handle this basically retirement and commitment of instructions. So yeah, if you want to learn more about this specific design of out-of-order processor, you can actually check this paper. And this is the machine that Tomasolo designed, IBM 360. We're gonna see a very similar thing soon that we want to, solve it, solve an example using a walkthrough example, basically. And this was IBM 360 in real world that people has been working. Okay, so yeah, let's recall also again this register renaming. So as we talked about it, we have anti-dependence and output dependence, that they are not true dependencies, and we fix them by register renaming. So the register ID is renamed to the reorder buffer entry or reservation station entry now, that will hold the register's value. So yeah, so basically register ID can be reorder buffer or reservation station and entry ID. An architectural register ID is physical register ID, and after renaming, reorder buffer or reservation station entry ID used to refer to the register. So these are the two differences that we're going to see also a lot now. Okay, so this is Tomasolo's algorithm that we're going to see. So we have this register rename table, also known as a register alias table or RAT. So if valid bit is set, you can see that we have a valid bit here for every register entry. If valid bit is set, the value in the table is correct. So this is the value of the register, basically. Otherwise, tag specifies where to find the correct value. Tag is a unique name for the value to be produced. Basically, tag is the idea of, for example, reservation station entry that we use for renaming. And it shows that basically the value of the register that we have here is not updated. And for that, we need to actually, the valid bit, we need to reset it. And we have a tag here, which is a pointer to the reservation station, for example. It's saying that the value of this register is going to produced by that specific instructions. So yeah, so for simplicity, we're going to ignore reorder buffer for now, but we see this RAT in detail here. So this is a Thomas-Solo's algorithm in definition of, so detailed definition. So if a reservation station available before renaming, basically instructions plus renamed operands, they need to be inserted into the reservation station. And we only rename if a reservation station is available. So if reservation station is not available, you shouldn't basically, we just stall, we wait. And while in reservation station, each instruction watches common data bus, which the bus that basically after execution, instruction put the value on that with the tag. When tag is seen, basically reservation station need to grab value from the source and keep it in the reservation station. And when both operands are available, instruction is ready to be dispatched. Dispatch instruction to the functional unit when instruction is ready. And after instruction finishes in the functional unit, we basically that needs to arbitrate for common data bus, because common data bus is a shared bus, and there might be several instructions that they finish the execution. So there should be kind of arbitration that who is going to put the data on that. So basically, every instruction that is done needs to arbitrate for that CDB, and then put tagged value onto the CDB. And register file is connected to the CDB. So register contains a tag, indicates the latest writer to the register, as we discussed. And then, yeah, basically register file is going to be updated by the tag value. And then we just need to reclaim, rename tag. Okay. So we want to do an exercise now. Let me see what's time. Okay. I need to go a little bit faster, but yeah.
Can you maybe tell a bit about where does the common data bus exactly come in? So where is it like connected to?
So we talked about broadcasting, right? We said that when the instruction is done with the execution, it needs to broadcast the value to the register file and reorder buffer, things like that, right? So when we cite, so for broadcasting, which means that sending to everyone, we have a common bus basically. So there is a common data bus that connects, is like a bunch of wires that connects all these memory structure. And it's common, so it's not like, you can write to this bus from different points. I mean, you can write from different points, but there should be only one writer at this certain time. So yeah, so that's the definition. But did I answer your question or not? Let's get back to this picture. Actually, maybe I can show you this common data bus. Yeah, there are many wires here. I'm not sure which one is common data bus. Maybe in this picture. Yeah, here we have it. So yeah, this one, after this floating point functional unit, functional unit, you have this common data bus that is connected. These load buffers, floating point registers. This bus is shared across all these units. And when you're done with your execution, you need to put your the output on that common data bus with the tag, such that everyone that is waiting for your tag basically gets updated and ready for the execution. Is that more clear now?
Yeah, it's a bit more clear.
We can also discuss offline. Okay. So this code that you have, so we assume that we have, for addition, we have a 4-cycle execution. For multiplication, we have 6-cycle execute. And we assume that we have 1 adder and 1 multiplier. How many cycles we need to run this code. So in a non-pipeline machine, it's going to take 50 cycles. I mean, by considering that basically we have we have 4 addition, and for each addition it takes like 7 cycles, right? Fetch, decode, 4 cycles to execute, and then write back. So yeah, it's 4 times 7, and we have 2 multiplication, and each of them will take 11 cycles. So in general, it's going to take 50 cycles if it's non-pipeline. When we have in-order dispatch pipeline machine with no forwarding and forwarding pass, and out-of-order dispatch pipeline. So this is actually the answer of that. I'm not going to cover it. You can actually check at home. So we're going to only cover the out-of-order one. So we can get from the 50 cycles. With the pipeline, we can get to 31 cycles. By adding pipeline passes, forwarding passes, we can actually get to 25 cycles, which is good. But with out-of-order execution, we can get to 20 cycles, which is much faster. And now we want to see how it works. So this is our first out-of-order machine simulation. So this is our register alias table that in the beginning, everyone is valid. And this is our tag, which is all are empty. And the values of registers is just the same as the register name, just for simplicity. So R1 is 1, R11 is 11, and so on and so forth. And we have 2 functional units. This is addition, and this is multiplication. And they have a reservation station, basically. This is for addition, and this is for multiplication. So initially, reservation stations are all invalid, and all registers are valid. So now let's go cycle by cycle. So in cycle 1, we fetch the first instruction, which is the multiplication. In cycle 2, we need to decode. So for decoding, we need to basically allocate reservation station, right? So the instruction is multiplication. So we need to reserve So we're going to reserve into this reservation station. So we check if reservation station available. Yes, we have plenty of empty spots. So the first one, X, is actually empty. So we access the register alias table. So we know that the multiplication is going to write to R1, right? So R1 is going to be produced by this instruction. So we're going to add the, I'm sorry, I just got confused. So multiplication is R1 and R2. So we read the value. So both of them at this moment are valid. R1 is valid. So we read the value here. So in the reservation station, the first source is valid and the value is 1. The second source is R2, which is also again valid, and the value is 2. And then we need to rename the destination register to X. So R3 needs to be renamed to X, and X is actually the entry of this reservation station. And it gets invalid, basically. So yeah, so R3 is now renamed to X, and its new value will be produced by the reservation station that is identified by tag X. Okay, now let's go to the third cycle. So the multiplication, since both sources are ready, basically it can happily get started. Yeah, since everything is ready, we dispatch and we start execution. For the second instruction, we are in the decode step, this addition. So we need to basically access, read R3 and R4. So we check reservation station. And since we have free spots, we use this reservation station entry A in the addition logic, addition functional unit. So the first operand is R3, and when we check the register file, R3 is not valid, so we use the tag. So we just enter the tag value here in the reservation station, just X. And for the value, we don't know, we will see later. And the second operand is ready. So we just add the value in the register reservation station. The output will be stored in R5. So we go to R5 and we rename it to A, basically. Okay. So we can see that this instruction, this addition cannot be dispatched because, yeah, one of the source is not ready, basically. So in cycle 4, basically multiplication still keeps executing. We need to stall the addition in the reservation station because one of the sources are not ready. For the third instruction, which is another addition, we can actually start it. I mean, start the decode step now. So the operands are R2 and R6. Sorry. We allocate basically reservation station B for these instructions, and we add the value of the operands to that reservation station. And we need to rename R7 to B, basically. This instruction can be dispatched for the execution because all sources are ready, basically. So in cycle 5, basically addition, the second instruction is still stalled. We can start the execution of instruction, the third one. And now we need to decode the fourth instructions. Again, it's addition, so we use the reservation station C. And the operands are ready again. So we add them to the reservation station, and then we can dispatch it for the execution. So yeah, basically we keep going. In cycle 7, basically all 6 instructions are now decoded and renamed. So what is here interesting is the last instructions, R5, addition R5 and R11, and the results going to be stored in R5. So you can see that here, basically R5 originally needs to come from this, yeah, exactly, from this instruction. So it's actually get renamed twice. So the first tag is A, because as a source value, this R5 is coming from actually this instruction, right? And this instruction, the reservation station is A. So the tag that we store here is A. And the second source is R11, and R11 is Y. But the output is also going to be stored in R5. So again, we need to rename R5. So R5 is going to be renamed to D here, which is the reservation station that we have here. So a bit confusing, but it's not really hard if you do it one by one. Okay, so yeah, at some point multiplication is done. So it needs to broadcast the value to all basically register alias table and reservation stations. You can see that this broadcasting is happening. And everyone that have the basically the tag X, they need to update the value. Yeah, too many animations. Okay, so now, for example, we don't have X anymore. Every X now is basically, we updated with the value 2. And we keep going like that. Yeah, I'm gonna flash these slides. Okay. So in cycle 9, you can actually, yeah, you can write back the first multiplication because you're done. And then you can actually start the execution of this addition because now you have the forwarding pass. And basically, the sources are ready for that, for this addition, basically, because it was waiting for X and now it's ready. And yeah, and so on and so forth. So yeah, it will go until cycle 20. It's just an example that you can go over it at home also. But this is so simple. So we did it together in the beginning of that. Okay. So There are some questions. But before that, any questions from you guys? Okay. You can also think about your questions maybe later and get back to me by email or in-person meetings, if you will. Okay, so basically what is needed in hardware to perform tag broadcast and value capture? So we make a value valid, and then we want to wake up an instruction. And that essentially needs lots of wires, comparators, and logics. So basically this out-of-order processor, they add a lot of complexity to provide better parallelism, basically, and performance. Does the tag have to be the ID of the reservation station entry? No, it could be any unique name that enables linking of producer to consumer. So it really depends on the way that you want to name things. So it doesn't necessarily need to be exactly reservation station entry name. So what can potentially become the critical path in this processor? So as you can probably imagine, like tag broadcasting, because there were many communication, right? One instruction finishes the execution, and then we need to broadcast the value. So tag broadcast, capturing the value, updating them, and waking up instruction. The whole chain is actually becomes the critical path of this out-of-order execution pipeline. And how can you reduce the potential critical paths? More pipelining and prediction. And actually, modern processors are actually doing lots of, pipelining, a lot of fine-grained stages, and makes a lot of prediction. For example, they make a prediction that which instruction is gonna, likely will produce the results in the next cycle. And then they can actually basically make it faster for transferring the result to the reservation station. So all this prediction can happen during the runtime. So I also have another example for you guys to do at home if you want. So when you have this kind of code, it's really easy to draw the data flow graph for the code. It's like you have a multiplication, basically the source operands and outputs. But what is hard is that we give you the state of the RAT and reservation station in, for example, cycle 7. And then we ask you to draw the data flow graph for the execution code, for the executing this code, and provide the executing code in a sequential order. So I'm going to also let you guys work on it at home. If you are interested, we have some exam questions about this. And we have some online basically resource that I can also guide you through them, that you can actually see the solution. But basically from this picture, you can reverse engineer the pipeline, and you can actually draw this control flow graph, as well as the list of instructions. So this can be a very nice question actually for the exam, probably, if you will. But don't worry, we won't have that much questions about out-of-order execution. Okay. So we cover a little bit out-of-order execution, but remember that we ignore out-of-order buffer. But now we want to also get back to that to provide precise exceptions. So we have out-of-order execution with precise exceptions. So the idea is that we want to use a reorder buffer to reorder instructions before committing them to the architectural state. So an instruction updates the RAT when it completes execution, also called the front-end register file. An instruction updates a separate architectural register file when it retires. So that's the key, actually. So we have separate, we have front-end register file, which we call it as a RAT, whatever you see. And we have a separate register file, architectural register file, that we update that when the instruction is ready to retire. So when it is the oldest in the machine and has completed execution without exception, we can actually update the architecture register file. Okay, and yeah, the architecture register file is always updated in the program order. Okay. So, and it's already been mentioned that when we have exception, we need to flush pipeline. We need to copy architecture register file into front-end register file, and then you know, do the. Basically, we need to make sure that we can resume from the exception handler after all. Okay, this is our initial out-of-order machine, like this reservation station and register alias table. We need to add this reorder buffer in between. And yeah, basically, the task of reorder buffer is very similar to what you have learned today. It's not really magic. So, and again, yes, we have this, now the pipeline is in order, that in fetch and decode is in order, but we have scheduling that provides out of order execution, and then we have in order dispatch, in order retirement of the instructions. And I like to recall you this beautiful picture, and yeah. So let's revisit very quickly what is out of order execution. So we need to link the consumer of a value to a producer. I mean, it's really important that you understand the basic, concept of out-of-order execution. The way that people design and architect, it is important, but it's not, to me, it's not that exciting. The exciting part is that learn about it fundamentally. So you need to somehow link the consumer of a value to the producer, and you need to buffer instructions until they are ready, like reservation station that we have learned about it, and keep track of readiness of source values of an instructions. And we talk about register renaming, reservation station. We also talk about broadcasting tags, and basically that instructions, they need to compare their source tags to the broadcast tag. And when all source values are ready, we need to wake up instructions and basically dispatch for the execution. So register renaming eliminates false dependencies, enables linking of producer to the consumer. Buffering in reservation stations enables the pipeline to move for independent instructions. Like for the tram examples, you could actually buffer a tram somewhere, and then other trams or cars, they can pass by. And the tag broadcast enables communication of readiness of produced value between instructions. Wake up and select enables out of order dispatch. So with out of order execution, we could actually enable data flow machine, but it's actually restricted data flow. Because in an out of order engine, we basically dynamically build the data flow graph, but of a piece of the program, not the whole program code. Any idea why it's not the entire code?
Probably the memory is just large enough.
Which memory? Yes, that's correct, but which memory? Reservation stations, reorder buffer. These memory they are limited basically in size, and at some point you cannot, you cannot make a data flow of the whole program. At some point you are limited by the capacity of those storage. So yeah, so the data flow graph is limited to the instruction window, we call it. An instruction window is all decoded, but not yet retired instructions. So can we do it for the whole program? These are some food for thoughts. If you are interested, you can think about it. Or also, you can also do some research, because there are some ways to improve this, but still we are limited. We're gonna also see something related to run-ahead execution, which was developed as a part of, as a Professor Mutlu's PhD thesis. I think we're gonna cover it on May 30, on Thursday. So yeah, so that lecture is gonna cover about prefetching and run-ahead execution, which is really interesting. So yeah, so there are these questions that for you to think about. For you, can we do it for the whole program? Why would we like to? Or in other words, how can we have a large instruction window? And can we do it efficiently with Tomasulo's algorithm? So yeah, there are several backup slides for you, more details on out-of-order execution, how we handle load and store, and also a little bit more about solving another issue that I didn't really went through it. Basically, we have a copy of the data, the same data many places, in reservation station, in reorder buffer, in register files. So the same value is going to be copied in many places because you broadcast and everyone copied that, right? So there are some ways actually to alleviate that overhead. And you can actually read about it if you're interested in our backup slides. And with that, I think we are done with today's lecture. And we still have 4 minutes. Any questions? Maybe now I can try to answer your question a bit more. If you can rephrase it a bit again, or I don't know. Or if you're interested to learn it about now, we can discuss it later as well. Okay, we can discuss it later. Any other questions? Okay, then enjoy your weekend and see you all next Thursday.